And this one go there first. So we are group 12 and we are presenting on the topic computer organization and architecture. First of all, we'll talk about computer organization. Computer organization deals with the operational units and their interconnections. Okay, so this basically tells us about how the computer system actually works behind the scenes. So let's think of an engine room where it covers hardware components like the circuits, data paths, and control signals. It also deals with physical connections between elements like CPU, memory, buses, and input and output devices. It also focuses on performance optimization, such as memory hierarchy and data throughput. So an example is when a CPU executes instruction, how the control unit coordinates with the ALU, memory unit, and registers is part of the computer organization. And let's move on to computer architecture. Computer architecture also refers to the attributes of a system visible to a programmer. Okay, so this also defines what the computer system is capable of doing. That is from the programmer's perspective. It involves instruction set design, what commands the system understands. It also specifies addressing modes and data formats. It's the abstract model that software developers interact with. An example is the Intel CPU's ability to use a particular instruction like add and how it's structured. So let's look at the importance of these two. It determines system performance. It also influences design of hardware and software. Okay, so designing efficient systems. The architects build instruction sets. Engineers organize components for optimal execution. And with the software compatibility, software must watch the architecture it's designed for. And for the hardware decisions, knowing how components communicate guides choices in building or upgrading system. So my fellow colleague will continue from here.
All right, let's focus on two very important but sometimes confusing concepts in computer systems. We have the computer architecture, which is the study of computer design and their interaction with computer hardware and software. It includes specifications like the instruction sets, data types, and then the number of registers. Um, While architecture defines the system, the organization focuses on how tasks are physically carried out using computer components. My fellow colleague will continue.
So we are talking about the components of a computer system. Here are the six main parts of a computer system: the input, the output, memory, control, ALU, and CPU. So the input devices like keyboard or mouse, they send info to the system. Make a show devices like keyboard share devices like keyboard or mouse send info into the system. The output unit, monitor or printer, they show results. The memory unit stores data and instructions. The control unit, they coordinate everything. So it acts like a system manager. The ALU handles the math and logic. CPU, known as the brain, it also runs instructions using the ALU and control unit. All this work together to process and respond to whatever you are doing on your device. So the next person.
Central processing unit. So the main components of the central processing unit. You have the registers, which they're small inside, they're fast storage inside the CPU. Then the ALU, it executes logic instructions. Then you have the control units, which directs the operations of the processor. Then coming to the instruction cycle, we have the first one. What it does, it has three processes: fetch, decodes, and execute. So for fetch, it gets action from the memory, and it takes it to the decode stage where it interprets the instruction. Then the final stage, which is executes, it performs the instruction, or it puts out the instruction or what it's supposed to do, basically. Yeah. I think the next person.
Okay, so the memory hierarchy, organized by speed and size. Registers, fastest, smallest, and also the cache, L1, L2, L3. And the main memory, that's the RAM. Also, the secondary storage, HDD or SSD. Tertiary storage, those are the optimal disk tip drivers. For faster memory, it's more expensive and smaller in size. Next person.
Yeah, so I'll be talking about the instruction set architecture. So this simply defines how a computer understands and executes instruction. And when it comes to the ISA, it deals with instruction format, which is how instructions are structured, data types, how the type of data which will be processed, registers, which are small, fast storage units inside the CPU, and the addressing mode, how the CPU locates data in the memory. Now we have two main types of the ISA, which is the reduced instruction set computer and the complex instruction set computer. And the reduced instruction set computer has some advantages over the complex instruction set computer because it's simpler and it has faster execution, which usually means less power consumption, unlike the complex instruction set computer, which is more complex and requires more power, although it can do work in a few lines of code. Some examples of the reduced instruction set computer are the ARM processors used in smartphones. And examples of the complex instruction set computer are the Intel and the AMD chips we see in our PCs. So next person.
Okay, so let's talk about pipelining in CPUs. We know that pipelining is a CPU technique that improves instruction throughput by dividing the execution process in separate stages. Now, so let's look at the stages involved in pipelining. We have the instruction fetch. Thus, we get the instruction from the memory. And then the next one, instruction decode, execute, memory, access, write back. So we get the instruction from the memory, and then the next stage, we understand the instruction, what it means, and then we execute. We perform the operation, which is the operation you want your CPU to, and then you can add and subtract. That's the executing parts. You need to perform the operation, and then the memory access. We read or write data from or to the memory, and then memory access writes back, we save the result to a register. And then let's look at the benefits of pipelining. So increase instruction executing rates. efficient CPU usage. Next.
So next we have the bus structures. So the bus structure in computer architecture and organization, bus structures are fundamental to the way different components of a computer system communicate and work together. A bus is essentially a shared communication pathway that transmits data and addresses and controls signals among the components. We have different types of bus structure. We have the data bus, which carries actual data between the CPU, memory, and peripherals. And it also characteristics are bidirectional, which data can flow both ways. The width, number of bits it can carry at once, directly affects performance. For example, 32 bits data bus can carry 32 bits in one transfer. Address bus, purpose, carries the memory addresses that the CPU can use to read or write data. The characteristics is unidirectional, from CPU to memory or I/O. The width of the address bus determines the maximum addressing capacity of the system. The control bus, the purpose is carries control signals used to manage the operations of the computer system. Examples of control signals, the read or write, specifies if data is being read or being written, and also interrupts control signals from I/O device to get CPU's attention. Clock signals synchronize operations, and bidirectional depending on signal type. Single bus structure. All components use one bus for communication, simpler and cheaper, but may become a bottleneck. Multiple bus structure. Separate buses for data and address and control, or multiple levels of data buses. Improves performance but increases complexity and cost. Why bus structure matters? It directly influences system speed, performance. Efficient bus systems reduce CPU wait times and improve communication between hardware components. Bottlenecks in bus design can significantly limit overall throughput, especially in high-performance systems. Well, real-world examples of this is modern computer. The CPU uses the address bus to locate where in RAM it needs to fetch data, and also that data is carried back to the CPU on the data bus. All of this is controlled by the control bus, which tells memory where it's read or write operation and when to it. That's all for the bus structures.
Charlie, you know how they do the organization.
You guys said hello.
Yeah,
Yeah, you are still doing the
you are doing the
I/O.
organization.
Okay. So for the organization, how system communicates with external devices. Oh, okay. So the organization, it refers to how the system to how a computer system communicates with external devices like keyboard, mice, displays. The goal to allow smooth, efficient data exchange between the CPU, memory, and peripherals. Why the I/O organization matters? The I/O operations are slower than CPU or memory operations. Efficient I/O management prevents the CPU from wasting time waiting for I/O devices, enhances system performance and responsiveness. Techniques for the I/O communication. The programmed I/O, how it works. CPU is actually involved in all I/O operations. CPU checks the I/O device's status and waits until it's ready. Once ready, the CPU transfers data. Well, the good side of it is it's simple to implement, and one of the bad side is that the CPU is occupied the whole time, inefficient, large or slow operations. Example, keyboard inputs where the CPU instantly checks if a key has been pressed. Interrupt-driven I/O. So how it works, I/O device sends an interrupt signal when it is ready. The CPU stops what it's doing, handles the I/O task, and resumes its work. Pros of the I/O, which is the good side, that the CPU is free to do other tasks until interrupted, more efficient than polling, better suited for multitasking systems. The bad side is that requires interrupt handling hardware and software. 3. Direct memory access. How it works. Special control transfers data directly between I/O devices memory, bypassing the CPU. CPU only initiates the transfer and is notified when it's done. The good side is that extremely efficient for large data transfers and pre-CPU during transfer. And we have that it's more complex. It's a more complex system. So that's for the I/O organization. Next person.
Okay, smartphone, sorry, real life example. So smartphones, they use the ARM-based RISC processors, which is energy efficient. Laptops, desktop, they use the Intel or the AMD CISC processors, which is more powerful. And the GPUs use parallel architecture for intensive computation. Everyday gadgets use different architectures for optimized performance, like the iOS, which uses the Mac uses it just developed a new chip. Yeah, which the Mac uses the M1 Pro or the M1 Max, M1 Ultra. So in a summary, architecture, what does the system does? Organization, how it does it. Key component, that's the CPU, central processing units, the memory, the I/O, the buses, techniques, which involves pipelining, DMA, and ISA. Thank you.